Hello, everyone, and welcome to the 9th and final lecture of the second edition of the Current Topics in Heritage Science series of ESR Academy. This lecture series is organized by emerging professionals in the frame of ESR project and the European Research Infrastructure for Heritage Science. My name is Fabiana DI Gianvincenzo, and I am a researcher at the Heritage Science Laboratory at the University of Ljubljana. I will be moderating today's lecture on the topic, The Illusion of Non-Destructive Analysis in Palaeoanthropology, delivered by Dr. Mathieu Duval. The recording of this lecture will be available on the E-RIHS EU YouTube channel. At the end of the lecture, you will receive a link to a survey. Please take a few minutes to complete the survey and let us know your opinion on the lecture. You can ask questions to the speaker using the Q&A function at the bottom bar of the Zoom window, which will be read to the speaker after the lecture. If you are experiencing any technical difficulties, you can contact us using the chat. I'm now happy to present today's speaker, Dr. Mathieu Duval. Dr. Duval is a Ramon y Cajal Research Fellow at CENIEH. He is a Quaternary Geochronologist specializing in electron spin resonance and uranium series dating methods. Over the last 15 years, he has developed an innovative research profile that combines methodological and datic application studies in geoarchaeological contexts. So far, most of his investigation has been dedicated to the development and application of the ESR and U-series methods to lower Paleolithic sites in the Mediterranean area. The results of his work have contributed to refine the age of some of the oldest archaeological sites in Southern Europe and Northern Africa. He has also recently participated to the direct dating of key human fossils from some of the most important known archaeological sites for human evolution. Thank you very much for accepting to give a lecture today, Dr. Duval. The floor is yours.
Thank you. All right, can you see the PowerPoint? Yeah.
Yes.
All right, thank you very much. All right. Well, good afternoon, everyone. First of all, I'd like to thank the organizing committee for giving me the opportunity to share the results of my investigation today here with you all. As Fabiana mentioned, I am a quaternary geochronologist specialized in ESR and uranium series dating. And I'm mostly interested in trying to refine the chronology and the timing of the early human occupations in the Mediterranean, meaning in Southern Europe and in Northern Africa. But today, I'm not going to talk about that. And instead, I'm going to present some results of another key aspect of my work, which is what we geochronologists call methodological investigation. In other words, basically, we work on the dating method itself in order to try to improve its reliability and its accuracy. We specifically try to evaluate any sources of uncertainty that may potentially bias dating results. And this is what the talk today is about. Behind this very catchy title, The Illusion of Non-Destructive Analysis in Palaeoanthropology, there is just a very simple basic question, which is to what extent micro-CT-scanning of fossils may impact ESR and C14 dating results. The results, yeah. Okay, I can change the slide. Perfect. So the results I'm going to show you today are part of a teamwork, and this is a work that was done in collaboration with my colleagues Rachel Wood from the University of Oxford and Laura Martin-Frances from CENIEH. And this research specifically originates from a misunderstanding, or at least an apparent discrepancy between my basic knowledge of radiation physics and the usual conception in paleoanthropology that micro-CT scanning is a non-destructive technique. As you know, human fossils are scarce and highly valuable. It is therefore essential to develop tools that are the least destructive possible. And in that regard, microtomography has become a very popular tool in paleoanthropology, and especially in virtual anthropology, in the sense that it can access the inner structure of dental tissue, of teeth or bones, without opening them. And it can also produce high resolution 3D images of these fossils. And the thing is, systematic micro-CT scanning of fossils has actually become a standard routine procedure in paleoanthropology. So micro-CT scanning has two main interests. Apparently, it is non-invasive and non-destructive. And these main advantages that are actually usually highlighted in many publications, like those two papers I just show you here at the bottom of the PowerPoint. What is the problem here? Well, the problem is that micro-CT is based on X-rays, right? So X-rays are generated in an X-ray source, then transmitted through the sample, and then recorded by a detector. The thing is, X-rays are a form of electromagnetic radiation, and especially they are usually qualified as ionizing radiation, which means that they carry enough energy to remove electrons from atoms, and they can change the chemical composition of the material they are interacting with. And previous investigations have shown that X-rays actually may induce a radiation effect on modern and fossil bones and teeth. There are two main instruments that are commonly used in paleoanthropology, what we call the commercial or conventional instruments, you have them here, the bottom right of the slide, and the synchrotrons. Just to give you an idea, a rough idea of the main differences between those two instruments, well, let's say that synchrotron beams are orders of magnitude more intense and brighter than conventional instruments. So today I'm just going to focus only on what we call the conventional instruments, which are the most widely used in paleoanthropology. So what do we know about micro-CT scanning potentially impacting fossil bones or fossils? From a previous study by Email and colleagues published in 2016, it seems that the conventional micro-CTs do not induce any significant impact on ancient DNA preservation, which led actually many people within the community to assume that micro-CT scanning was not causing any damages to fossils in general, which is not totally true, because when we look at the evidence available for ESR dating, what do we see? Or what do we know? Well, first we know that X-rays do produce a radiation-induced ESR signal in the enamel. We also know that conventional micro-CT scans may introduce a dose of several hundreds of grays in the enamel. So we know that potentially micro-CT scanning may impact ESR dating results. But the thing is, or the problem is, to try to quantify this impact. Before reaching this step, we should first wonder why we bother actually with ESR dating. Well, simply because it's one of the very few methods that you can use to directly date fossils. Okay, if you want to date fossils, directly date fossils, you don't have a wide range of methods available. You can obviously use radiocarbon, which is the most standardized method, but this can only be used for fossils that are younger than 40 to 50,000 years. Okay, if you want to directly date Middle Pleistocene fossils, for example, you can use uranium series here, uranium thorium in green, but this method is only going to give you a minimum age for the fossil, because what the event that is dated here is the incorporation of uranium into the fossil. Okay, and this incorporation systematically post-date the death of the organism. So if you want to get a finite and direct age result on a fossil, the only option here, especially if the fossil is older than 50,000 years, the only option is to use ESR data. There are a few examples actually to illustrate this, like the study that we performed on the Homo antecessor remains from Mathieu Duval in Spain. with the layer ED6 here, that was dated to the latest part of the early Pleistocene, using a wide range of methods like biomagnetism, luminescence, and ESR. And we actually dated a fossil tooth from Homo ancestor, like this one here, using ESR, and we got an age that was consistent with the other methods, confirming the antiquity of the fossil, and the fossil being between 0.8 and 0.9 million years old. Another example is the work that we carried out on Miss Leah, for example, which is the oldest Homo sapiens found outside of Africa. And in this case, the use of ESR dating enabled to get direct age constraint on the fossil to about 180,000 years. Another example of dating study I use based on ESR, on the ESR method, is the this very peculiar fossil that was found in South Africa from the Rising Star cave complex, which was dated using a double-blind approach, which means that actually the same teeth were dated independently by two different labs, and both providing very consistent results of between 230 and 330,000 years. So these examples are just to show you why it is important to improve the accuracy of the ESR dating methods. For those who are not familiar with the ESR dating method, well, here just one slide, just to summarize the basic principles. ESR stands for electron spin resonance. It is a paleodosimetric method. And in this case, the sample, the tooth, acts as a dosimeter. So the tooth, when buried, actually, is going to absorb radiation from the surrounding environment. This radiation can take the form of cosmic rays, alpha particles, beta particles, and gamma rays. And to get an age, we need to evaluate two parameters to the ESR. The DE here, which is the total dose, total radiation dose absorbed by the tooth over time, and the D, that is the dose rate, or let's say the intensity of the natural radioactivity around the sample. What matters here in this talk today is how we evaluate the DE, the equivalent dose. Basically, when the tooth enamel is absorbing radiation, you will have the creation of a scene that you can measure with ESR spectroscopy. On the graph here on the right, the middle one, you can see typical ESR signal that you can measure in tooth enamel. And you can see the intensity of the signal is increasing with the dose. The peaks, the heights of the peaks, T1, B1, B2, is increasing with the dose. Okay, so the more dose your sample is going to put, the higher will be the intensity of the signal. When you plot the intensity along with the dose, you can build what we call a dose response curve here. And by extrapolation of the dose response curve, you can estimate the DE, which is the total dose absorbed by the sample over time. Based on this very basic explanation, you can, I guess, understand that any post-sampling irradiation may potentially affect the accuracy of the dose and estimate. So in theory, micro-CT scanning of two samples will induce a dose overestimation and will potentially artificially age the ESR results. But to what extent? This was
Dr. Duval?
Yes.
Excuse the interruption. Your sound is a little bit muffled at times, so I think there is something with your microphone.
Yes, maybe. Not sure what I can do. Do you hear me?
It's still quite muffled.
Let me try to disconnect and reconnect the mic. Can you hear me?
I think it's much better now.
Is it better?
Yes.
All right.
Yes. Do you mind repeating the last part of the explanation?
Yes. So, okay, I'm sorry about that. My point here is that any post-sampling irradiation of the sample of the fossil may actually potentially affect the accuracy of the dose estimate. Okay, so what I want to emphasize is that the micro-CT scanning of fossils may potentially induce a dose of estimation and thus artificially age the ESR result. But the question is to what extent? So this is what we actually try to quantify by running a series of micro-CT scanning experiments. So we took a modern tooth, basically, that we divided in 4 subsamples. Samples 1, 2, and 3 were micro-CT scan, and samples 4 was not micro-CT scan. We kept it as a controlled sample. Samples 1, 2, and 3 were scanned using the standard acquisition parameters that we use at CENIEH, depending on the degree of fossilization of the remains. So the first set of acquisition parameters is what we usually employ to date modern humans. Second set is what we use to scan middle Pleistocene to late Pleistocene fossils. And the third set of acquisition parameters is used mostly for highly fossilized remains. Basically, just to give you an idea of what is the main differences between those sets of parameters, it's just a matter of voltage and amperage. So there's an we use increasing values of voltage and amperage, depending on the fossil or the fossilization degree of the remain. And for all the sets of parameters, we use metallic filters. So what did we observe? Well, first, here on the bottom left, we clearly observed what I showed you before, a radiation-induced ESR signal, the same that we can measure in samples that you find in the nature, okay? So sample 1 is in black, sample 2 is in red, sample 3 is in green. And you can see clearly that there is an increase of ESR intensity. And just as a comparison, you can see that in yellow, this is a control sample that was not micro-CT scan. So we are talking about orders of magnitude of differences between the CT scan and non-CT scan samples. We try to evaluate the dose of the micro-CT scanning, and we established our dose response curve, as I mentioned before, and we found effective dose, or we calculated effective dose values of between 16 and 26 grays. So what does this value of 16 to 26 gray mean? If you take some case studies that have been published recently, like the tooth from El Cidrón in northern Spain, the published geological dose was 32 grays. So if you add on top of that the 20 grays approx generated by micro-CT scanning, you would potentially artificially age your ESR result by 62%, which is massive. If you look at another example, like the tooth from Banyoles, which has been dated to 66,000 years, you can see that the published geological dose was around 155 grays. If you add those 20 grays on the micro-CT scanning, you would artificially age your sample by 12%. And if you select an older tooth with a much higher dose, like this one from nowhere, for which a geological dose of 813 grays has been estimated, you would only artificially age your sample by 3%. A couple of very recent case studies to show how this can actually impact our dating results. The study of the Mislia remains that I mentioned earlier. The problem with this remain is that it had been previously micro-CT scanned several times in different institutions and with unknown acquisition parameters, basically. So we knew that it has been micro-CT scanned, but we were simply unable to estimate the dose that was given. So we could only get, in this case, a maximum ESR age. Another example to illustrate the variability of this impact is, the work that we did on Atapuerca Grandolina in this case. So in this case, the scanning conditions were known. we knew on which instrument and with which parameters the micro-CT scanning had been performed, and we estimated the micro-CT scan dose to about 10 grays. So if you compare that with the 750 grays that we estimated for the geological dose, it means that the micro-CT scanning would only have a minimum less than 2% on the dose. Just to show you the variability of this impact, depending on the fossil that you want to date. We also estimated the variability of this impact using different instruments and acquisition conditions. Another experiment was performed without metallic filter, which returned a dose of more than 150 grays. Okay, so it's about 8 times higher than what we obtained in the previous round of experiment. For the third experiment, we used a different instrument with different acquisition parameters, and we got a dose of about 10 grays, which is about 6 to 7 grays lower than what we got in the first instance. Okay. What can we conclude based on these results? Well, first we can conclude that conventional micro-CT scanning does have a non-negligible impact on ESR dating. The magnitude of this impact depends on a series of factors, such as the initial geological dose, but also the experimental conditions. Basically, the older the sample, and the lower will be the impact on the age. The amount of X-ray dose that is absorbed by the sample is instrument and lab procedure dependent, because there are many sources of uncertainty involved. The X-ray source, the type of source involved, the distance of the sample to the source, the irradiation time, for example. So it is impossible to get a universal conversion or correction factor. You will need to specifically assess this dose for each device and set of parameters employed. Therefore, we would recommend not micro-CT scientists in case they are intended to be dated with ESR in the near future. We do understand that it's not always possible, so in this case, we would then recommend just to micro-CT scan a modern tooth with no signal, basically no research signal, following the same exact procedure as the one that was employed for the fossil sample. This is the best option actually to estimate the micro-CT scan dose that will be given to the sample and subtract it from the geological dose that we are going to estimate later. Hope this makes sense. Based on that, on these testing results, then we wonder, okay, but what happened with radiocarbon dating, for example? I mean, micro-CT scanning should not, in theory, impact radiocarbon dating result, but still, it's worth checking. So we selected 2 samples. One bone from a Russian locality with the MIS5 age, meaning that it's much older than the C14 time range. And another tooth that was a modern tooth from in France. We use the same instrument and the same acquisition parameters as in our previous study. You can here see an overview of those parameters. And the collagen was extracted using the ultrafiltration protocol at the Australian National University. And the samples were dated by radiocarbon. So what did we get? First, in terms of age, the bone samples written radiocarbon ages older than basically 42,000 years, which is consistent with the known age of that bone, which means that there is no significant impact of micro-CT scanning on the radiocarbon age, which is good. However, if you look at the collagen yield, this is another story. The collagen yield is actually evaluates the quantity of collagen that can be extracted from the bones or from the teeth. It is used as a proxy to estimate whether a sample actually is well preserved or not, and whether it can be dated or not. Just to give you an idea, a modern sample would provide a collagen yield value of around 22%. In fossil samples, if you have a collagen yield of between 6 and 8%, you would consider that with the good preservation of the collagen. If the value was between 3 and 6, you would consider that it's a low low preservation. If it's between 1 and 3%, you would see it as a poor preservation. But still, the sample would be dated. If the value was below 1%, then you would regard this sample as poorly preserved, and the sample will not be dated. Based on this very basic concept, let's say, you can see the result that we got here on the bottom right on the graph. Okay. In black, you can see the unscanned sample. And in red, the scanned sample, bone and for the dead. So first of all, if you compare the black and the red, you can see there is clearly a decrease of the collagen yield. It's a reduction of by 30 to 40% of the collagen yield. This means that there is clearly an impact of micro-CT scanning on the collagen preservation. In order to evaluate whether these differences could partially come from some heterogeneity within the sample, we also decided to plot the same sample, but that was pre-treated previously at other times, just to see what value that we got in the past. And you can see that all the values actually show some pattern indeed, but they are all systematically higher than what we got for the scan sample. When we try to plot the same results along the voltage and the current values, this is what we get. And we can actually observe that there is no specific correlation between the voltage of the current value with the collagen loss. In other words, it doesn't matter whether you actually use a voltage of between 80 to 180 kilovolts or a current of between 100 and 300 microamperes, you get the same collagen reduction. And still, this reduction, this collagen value is still lower, obviously, than the unscanned sample that you can see. So, it seems that the reduction in collagen is actually maybe related to the combined effect of the radiation damage and the collagen extraction post-radiation. It is possible that the minor damage induced by ionizing radiation may be amplified during the analytical procedure and the sample prep in particular, culminating in the removal of a greater portion of the smallest fragments during ultrafiltration. So what are the implications of this result? First, it means that maybe a larger sample may be required for C14 analysis from bones or teeth that have been previously micro-CT scanned. This should be kept in mind. Samples with initially a very low collagen yield might also become unsuitable for C40 dating after micro-CT scanning, simply because they provide a collagen yield that is below the usual minimum cutoff value of 1% that I mentioned earlier. So it would be viable actually maybe to relax the percentage of collagen yield quality insurance for micro-CT scan fossils. What would be the main...
Dr. Duval?
Yes?
Sorry, this is your 25-minute mark, heads up.
Perfect. Okay, that's my last slide. So what would be the take-home message? First, we should make a distinction, I think, between the fact that a technique does not cause any visible damage of fossils and the fact that we would consider it as non-destructive. If you want to read more about this, I would recommend you to have a look at this paper here, for example. It is clear from our experimental results that micro-CT scanning is a destructive technique, okay? And it does have a non-negligible impact on fossil preservation and associated with dating results. For radiocarbon dating, it does affect the collagen preservation, and for ESR, it does artificially age on the sample. Please be aware that this is just the tip of the iceberg, meaning that the impact of micro-CT scanning and other analytical techniques remains unknown. Okay, this has been very little investigated. And even worse, we don't even know what may actually happen other techniques that are going to be developed in the near future. So we should be very careful about that. We should keep that in mind before microscopic scanning fossils. Simply because X-rays have irreversible and cumulative effects. Once the sample has been irradiated, it's impossible to go back or to reverse the effects. The more you scan the fossil, the higher the radiation rate and the radiation dose will be, progressively erasing any kind of useful information that is contained within the fossil. There are some basic recommendations that we can do. And in that sense, I would also recommend you to have a look at the conclusions by Email et al. Published in 2016. But basically, this would be trying to minimize the radiation exposure. This can be done by using a metallic filter, for example, but also to try to avoid repeated microscopy scanning if it's not necessary. Not to work at higher resolution, not needed as well. And it is also essential to record the scanning history. I mean, the type of instruments used, the acquisition parameters employed, etc., in order to know or at least be able to estimate the total dose accumulated in the sample and also facilitate maybe data sharing when possible. So to conclude, we would simply recommend extreme caution regarding systematic and unlimited use of microscopic scanning in paleoanthropology, or actually in any other related disciplines involving fossil material. Thank you very much for your attention.
Thank you, Dr. Duval, and thank you everyone for joining the lecture today. While we give everyone some more time to write in their questions, I would like to announce what will happen in the HS Academy in the autumn. This was the last lecture of the second edition of the Current Topics in Heritage Science lecture series, and I will take a chance to thank again all the great speakers that contributed to this edition. We are currently planning the third edition that will start in the autumn, so I invite all of you to stay tuned via the E-RIHS website and social channels. Thank you.